So we're back. Today I'm just going to continue writing our Wasm encoder inside PureScript. In case, well, I mean, I could just talk about what we managed to get going last time around. So what did we do really? We managed to write a binary, a Wasm binary with a custom section with a name. And that's exactly what this is doing over here. So we're saying write module, we're writing a header, and we're writing a custom section, and then we're writing the whole thing to a file. And that's what we managed to do yesterday. Today I would like to try and manage to use this encoder to encode an actual piece of code. So rather than just an empty section with a name, I would like to encode the function, code, and type sections that we need to have a Wasm module that has some logic in it, some actual code. Right, and we'll just keep going through the spec really here, and implementing things as we need them. I'm just going to turn on the music a little bit. All right, cool. So we ended up reserve size byte, reserve section size. That's a bit weird. I'm going to call this one reserve section size as well, because these are supposed to basically always be used together. And then we're just going to find the other call set of this. This is going to be reserve size. Wait, that's going to be reserve section size. Like so. Here we go. Okay. And so now I would like to start working on the type section, I believe. So here we just wrote a custom section, but this one is kind of, well, hard coding the thing that's actually being written here. We're going to end up needing a PureScript type for a Wasm module, but for now I'm also just going to hard code what the type section is writing. And it takes a debuffer and returns an effect unit. And for now, we're just going to stop that one out. And then we're going to read about what the type section contains. So the type section has the ID 1. Okay, that's something we can start with. So what we're going to do, we're going to write a section with the ID 1. And we are going to write this. What's the second parameter? Oh, B. Okay, so B1. That's what we're going to do. And then in here, well, this is the bit where we actually write the type section, but we haven't filled that one in yet. So a type section has the ID 1. It decodes into a vector of function types that represent the types component of a module. Okay, so there's a bunch of stuff we need to think about here. But from a pure implementation point of view, this is the bit we care about. So this is a section that contains a vector of func types. Okay, so we're going to need to figure out what a func type is, but let's just say for now that we're only going to encode a single type, and that's going to be a type that looks something like this. Okay, let's work with eyes here because that's easier. Okay, so we're going to need to write a vector. Now we're going to need to add the elements of the vector, and there's just one type here, and this is the one that we need to figure out how to write that bit, and that is, we're going to figure this one out by looking at how func type is encoded. so func type is down here. Function types are encoded by the byte x, so 60, followed by the respective vectors of parameter and result types. Okay. So result types are vectors of val types, as you can see from here. Okay, so but we know what we're going to need to do first. So the first thing we're going to need to do is we're going to need to write a we're going to need to think about this. So we're going to need to write a func type essentially. We don't have that function yet, but we're going to write it, which is also going to accept the debuffer and return effect unit for now. And really what this is going to eventually accept is also the func type it's supposed to write. But for now we don't have that, so we're just going to say write func type here. And what func type is going to do is it's going to write the byte sequence, so 60 in, so 0x, so like 60 in hex, which is 6 times 16. I don't even know what that number is, but whatever. We're just going to write that. So we're going to write a... is this a single byte? I don't think so, right? Add int 8, but that's a larger number than an int 8, I believe. And isn't this like 2 bytes? Might be wrong. Probably isn't right to say. Yeah, that's probably fine. It's 96. Okay, so that should work. We should be good. I'm gonna figure this out if eventually we're gonna need to be able to write larger things than that. And this is probably gonna take the buffer as the first argument. So we're just gonna write 0x60, and now we're gonna need to write 2 result types. And I'm gonna again follow the spec here. Both of these are gonna accept a buffer. And so write result type is going to take a debuffer and return the effect unit. Like so. And then what a result type is a vector of value types. Okay, so we're going to write a vector of value types. And for now, I've decided that this value type is just going to be always going to be in I32. Right, so we're going to write a function from I32 to I32, and eventually this is going to be different, but for now we're just going to add int 8 for what really we're going to say. Yeah, I'm just going to hardcode this and then we're going to figure it out eventually. So I32 is 0x74. And we're going to write that into the buffer, like so. I'm hoping that that's going to work. Now what I'm going to say is rather than just writing the custom section, well, I'm going to write the custom section first, and then I'm going to write the type section. Okay, we're going to write that to a file, and I'm hoping that if we look at the output of that we'll get some more information. So npx spargo run. How does that work in PowerShell again? I think that's the semicolon. Yep. Invalid value type. Error. Expected value param type got 0x minus 0xc. Okay, is one of these too large? Value types are encoded by a single bytes. Encoded by the byte 0. So these are single bytes. That should be fine. I'm gonna need, and then I'm gonna write the result type twice. It's gonna be a vector, right? Or is there are encoded by the respective vectors of value types. Exactly. And the val type is this thing. Value types can occur in context where type indices. Thus, the binary format for types corresponds to the signed LEB 128 encoding of small negative values so that they can coexist with positive type indices in the future. Well, I don't care about that. I'm just going to write the byte, right? So when I wrote the func type, did I do the right thing? I write one of these, and I write both of these. Right? Looks like that to me. In the function section, did I end up doing that? That wrote the type section, wrote a section 1 with the func type. Wait, no, it's the type section, yeah. What if I don't write the custom section for now? Same problem. Expected valid param type got minus 0xc. Is there something about these bytes that we're writing wrong? So we write 0x60. Then we write the two result types. Result type is just a vector of value types. We write a vector here, value types. So this console log is of course wrong now, but let's call it vec length. And let's just, for the heck of it, accept a string here which helps us with debugging. So we're going to say vec length for something. So the message in here, and we're going to say do this like so. Now we need to fix up all the right vecs that we do. So here we write a vector which is the this is an actual string, so this is custom section name. So what's this one? This is the result type. Oh wait, is this where it's gone wrong? No, it should be. And this is the type section. Okay, so let's do this again. So the length of the custom section name is 2, type section is 1, result type. That's right. Both of these, all of these seem correct. Okay, so let's look at the reference implementation because I'm not entirely sure anymore. So where is the... So value types are encoded as variable signed 7, which is very different. Okay, so this is using variable length encoding for types. Is that what this is? What does this mean? What number is this? This is 127. So this is all ones. Which I think, is that the problem? What if we were to say these are 7 E's? Does that change anything? Oh wait, this needs to be an F, of course. That's what's going wrong. Numbers are hard. Okay, here we go. That worked. So we have a custom section. We have a type section. And this type is this type. which is the type of the function I want to encode. So that sounds great. All right, cool. So we're writing that. And again, we're going to create a type for these things. So that we're actually encoding something useful, not just hard coding things. But for now, I just want to write a Wasm module that does something. And then we can figure out how to write useful things, essentially. Okay, so type section is figured out. So the next thing, are we still in the binary form? Yes. So we need a type, and then we need a function which matches functions to types from the type table, I guess. Type indices. All of these are just U32s. Oh, we do need to encode that correctly, but we'll figure that one out. So this is just a vector of type indices, so just a vector of ints. Well, let's try that. So this is not the type section, this is the function section. So we're going to write the function section. I'm going to write it with the index 3. And this is the function section. Okay, so what do we write? We write a vector of type indexes. And that's just the one here. So I'm just going to add an int 8. Just 1. No, we need 0, right? Yeah, because the index of this thing is 0. So I have a feeling that when I do this, it's going to complain. But let's try. So I'm going to write the function section like this. I think it's going to complain that the code section does not have a corresponding entry. Function count is 1, but code section is absent. There we go. So this is, but this is declaring that the first function matches the signature 0, which is this type. So that's what I was expecting. So that's good. So now what we need to do is we need to add the code section for this function. This is the interesting bit. This is where things are going to become tricky and fun, I think. Well, it was reasonably tricky up to this point. Okay, so we're going to write the code section. And the code section is a section with the ID 10. Okay, so what is the code section? The code section, it goes into a vector of code entries. Okay. So the outermost thing is going to be a vector. And everything I want inside here is going to be a write code. I'm just going to write code once for now. Okay, so what does write code do? It takes a buffer. Well, all of these functions do this for now. So the code is a size in U32s. Okay, what does this mean? The size of the function code in bytes. So this is the same thing that we were doing with the section size, right? We're going to reserve a size and then we're going to write it afterwards. Okay, so let's try that. So we're going to say, I'm going to reserve. So wait, what does the code section do for step 1? The first thing it does is it reserves a size. Okay, so size offset. It's going to be reserve section size, well, which is no longer correct because we're just reserving the code size now rather than section size, but that's fine. And eventually we're going to say we're going to write, did we say write? what do I call it? Reserve section size, write section size. And this is going to accept a buffer. Then it's going to accept the offset and then the actual size. So this is the size offset. Okay. And then the size is going to be end minus start, similar to how we did this over here. Like so, just that in the middle here, we're actually going to do something, which is we're going to write a func. Like so. Just going to write this out so it compiles. Does not like this. Oh, because I wrote the size offset twice here. Yes, that should work. Okay, so why does it not like this? This needs a B. Okay, that works. Okay, so how do we write a func? What is a func? A func is the declaration field of locals, the function body as an expression. So locals are U32s and their types. Okay. I think so anyway. It's going to be a little weird. So a vector of locals. So I'm going to write a vector and we're going to call this func locals. And the locals are going to be a, so we're going to again, we're going to write an int by hand here. Because the function I'm thinking of has exactly one local. So we're going to say, we're going to write the local one in there. And then, this is PureScript. And then we are going to add the value type. Did I write this out? This is a value type, right? So again, I'm just gonna leave this as is. We're gonna write it properly in a bit. I just want something to run here first. So right, no, just one add-in should do it, like so. What do you not like about this? It's an array of effect. Yeah, but this accepts a B first. So a vector of locals, and locals are just these things. And the length of this vector is exactly 1, which it figures out by hand, or like by itself. And then after we've written this vector of locals, we need to write the expression. And this is the interesting bit. So write expr. Going to accept the debuffer and return effect unit again. And I have a feeling that now, well, we'll figure it out. So expr. So now we're in the core syntax. No, I need the binary format of this thing. Okay, so here we go. Now things are getting interesting. Expressions are encoded by the instruction sequence terminated with an explicit 0x0b opcode for end. Okay, so we're going to write a bunch of instructions followed by the thing that terminates it, essentially. Okay, so we're going to start by saying add int 8, and the end is 0x, okay, so 0b. That's the end. And now we just write the instruction sequence. And if we recall what program we actually want to write, there's the over here. This is the expression I want to write. So I've got local.get and $x here is 0 because this parameter is 0. And then I want to put a constant value on the stack, and then I want to call add. Okay, so we're going to look for local.get. Okay, so I'm wondering, I think this is probably fine. So variable instructions. Instr. These are control instructions. Okay, yeah. So we're just going to write out the stuff we care about. So we get local.get, and then we need an ID. So okay, so here's what we're going to do. Okay, so let's write this. Where are we going to write this though? Write exporter. Here we are. So the first thing we're going to do is we're going to write local.get 0, which is going to be, so what are we going to add? We're going to add local.get, which is x20, so 0x20, and then the ID is going to be 0. Okay, so what's the next thing we're going to do? We're going to add a const value. So const, this is memory instructions, parametric instructions, control, numeric instructions. So const, here we go, 0x41. So now we're going to do this. So what's the first instruction we write? 41. And then we're going to just going to write the value 10. And all of these actually have to be LEB 128 encoded, but we're going to do that when we find a time. Okay, and so the last thing we need to do is we need to add the instruction for add, which for i32 add in particular, and that's 06A. i32.add is 6A. That's i32 add. Okay, so and that should be it, and that should be this is the explicit end. And again, I think this should be the right code section. And I think this should match. So there's the code. All right, now can I actually call this somehow? No, I need to add an export. Okay, so let's write the export section real quick. So we need to write the export section. Has the ID 7. It decodes into a vector of exports that represent the export's components of a module. Okay, so 7. 7 is, let's look at this. Code is here. So export is before code. So we're going to write the export section at about here. Like so. And then we're going to go about here. So write export section. And if you have any question, just ask, right? Just ask away. All right, cool. So let's figure this one out. How do you make an export section? Here we go. Export section. Exports. Oh, that's what it's defined syntactically. So this is the export section. Here we go. So an export section is the section number 7. and it is a vector of exports. And exports is a name followed by an export description. Okay, so we wrote a name somewhere already. Name. Here we go, custom section name. So this is what we did before. And this was PS. Now I want to write the name, some other name, essentially. So let's just write an export, right? So write export. So we need to do something. Oh, damn it. Something like this. So this writes the name. We're just going to write the export name here. And it's not going to be PS. Actually, I want this to be add 10. But maybe just add is easy enough for now. So just a small a dd. I just want the ASCII table essentially. Okay, so what's the small a? Small a is 6.1. Now we need 2 D's, which are 6.4s. I'm just going to do that twice. Like so. I hate this formatting, but okay, I can make the edit to do something acceptable. Never mind. So this should say add, which is the ASCII, the export name. And then after the name, we're going to write an export description, which is one of these. And so we're going to write a function ID here. So we're going to write a 0. And then we're going to write the ID of the function, which is also just going to be 0. So the function 0, because that's the first function we defined, and that's supposed to be called add in the export. Okay, so let's try that one more time. Okay, so we're exporting function named add. Okay. And so what we should be able to do now is we should be able to say wasm time dot byte wasm bytes dot wasm. Okay, that works. And then we're going to say I don't remember the command anymore, but maybe it does. Okay, so run, and we're going to say bytes, and this is probably way too far down. You can't read this. Just gonna move it to the top, sorry. So bytes.wasm, and then we're gonna invoke the function add, because we call it add. And this returns 48, which is not the number I was expecting. Oh no, you didn't know you know about what before. So you could compile to what, then compile what to wasm. Yes, you could, but that's kind of bad. Because, well, the binary format is supposed to be the thing you generate. It's like optimized for being generated, so you don't want to create text and then have some other compiler like break it down again. That's what I used to do, compiling WAT, but yeah, you shouldn't do that actually, if possible. Okay, so why is this going wrong? because this adds 16 rather than 10, and I think something here must be going wrong. So let's check the I32 const thing again. That's the instructions bit. The code section. Code, which is func expert. Here we go. Wonder what you use what for then? Well, for handwriting. Okay, Wasm. That's what you use it for, and to write tests and these kind of things, right? Yeah, handwritten Wasm, similar to how a compiler does not generate assembly, as in like it doesn't generate the it doesn't type out move or something. It generates the actually binary thing that that stands for. But we still, when we look at assembly, we try to as a human read assembly, we look at a textual representation of it. So const, that's what we did, right? 0x41. And then an I32. Oh, right. This is a signed one, right? This is an assigned, which uses a 2's complement resolution. But I think we should be inside this region. So I think this should just be 10. What we can actually do is we can disassemble the Wasm we generated. Right, we could do that. So there's a Wasm to wat, which generates the textual format from a thing. But we're writing a const 16 here, so that's exactly what's going on here, which is surprising. So, well, we'll have to understand the LEB format for signed integers, really. Which is probably going to be a tiny bit trickier. But we'll get back to that. So, but I mean, really, what we can see here is that we're actually generating the thing we kind of want to generate apart from this bit. But this all looks fine. Like this looks exactly like the code and the module we wanted to define. So I think we figured out all the important bits. The tricky, I'm going to take a tiny break, I think, and then I'm going to look into just a quick break, like 5 to 10 minutes max, maybe 5 minutes. And then we're going to look into LEB 128 proper for signed and unsigned integers. And once we figure out that, has LEB format been the hardest thing about this project so far? Not at all. No. LEB is fine. LEB is, I know it's kind of the only reason why it's kind of hard is that I'm not used to bit fiddling at all. I think the hardest part really has been figuring out how all the Wasm parts play together, and it's kind of hard to debug binary stuff, I guess. It's just because the output is just bits, so it's kind of hard to tell when something goes wrong because you can't really step through and make sense of the data. I think that's the hardest part. And we might want to figure out how to wrap this up because we're passing the buffer around so much, but maybe that's fine as well. Maybe that's not a problem. Yeah. I don't mind the LEB thing. I kind of think that's actually an interesting problem because it's like small and tiny and you can easily unit test it. So I'm kind of looking forward to that. Yeah, but let's do that in like 5 minutes. I'm just going to grab a coffee and yeah, and I'll be back. Do I have a pause thing in here? Probably not. All right, cool. That's nice. All right, I'm just gonna write it in the chat. 5 minute break. I should maybe make an overlay or something for this, but yeah, I'll be back in a bit. All right. I am back. I made a scene in OBS, which was a black screen with a taking a break text on it. Came back 15-20 minutes later, and all my Twitch connection showed error messages and my stream was stopped. Oh, that sounds terrible. Breaking the rules somehow. I don't know. Well, luckily, I think the stream didn't die here, so we can just keep going, I guess. Cool. So what did I say what we're going to do? I said we're going to do LEB, right? So LEB 128. So let's do that. So I guess we're going to say unsigned. Well, let's just LEB 128 this thing. So what we get is an int, and actually Wasm supports numbers much larger than ints, so we can go all the way to 64 bits. It's kind of a problem because, well, in JavaScript we can't represent those. Yeah, understandable. I mean, the whole streaming thing is a very bandwidth intensive problem. So it's actually very nice that we have these streaming services. Okay, so but we're gonna do LEB 128 for int32s, I guess. And then binary type. It's such a rare occasion. Yes. Well, in the recent few streams we did, we basically never did any binary things, and so we can figure this out from the definition, or we could look at an implementation and just copy it. What would you prefer? What are we even going to do here? I mean, we could just make this. This is a pure operation, right? So we don't really need to make this effectful. We could just return an array of int. You know, it kind of feels bad. Let's just do an array of int for now, and then we can figure it out. So every single int here is supposed to be a byte. So copy paste. You would copy paste. So my question is, do we do that, or do we figure it out? Not what would you do? All right, no comments, so let's copy paste it. Okay, so we're gonna need to use the VUs, which are, I would need to understand everything. Okay, we're gonna figure it out. Come, let's just look at Wikipedia. And we looked at this before, right? What we do is we break a number up into individual 7-byte long stretches. And then we keep writing. Stream is delayed like 15 to 30 seconds. All right. That kind of sucks. Maybe my chat was lagging behind. Probably not. I'm gonna check out on Twitch how far I'm behind, just to make sure that That's actually what's going on here. So it's loading. So for me, it's like I can hear myself a second after I say something. Yeah, so I just checked out on Twitch and there was like basically no delay. Maybe you need to refresh the page. All right, so what's the goal here? The output stream is 0xe5, which is this thing. And it is that because this has been set to true. So the way I see this, what we do is we say the 7 bits is equal to x, and now we need to use bits dot and now we need the thing that is just the last 7 bits. I think that's 0x7. F. I'm starting to remember these numbers. It's a little scary. Once we've done that, we need to shift the whole thing by 7 bits, and then we need to check if it's 0. And if it is, we can stop there. If it's not, we need to set the 1 bit and write it and keep going, I think. Let's shift it. We're going to shift the thing. Shift left. No, we're going to shift it to the right by 7. Okay. And now we're going to check if shifted is equal to 0. Then we're basically done. So all we need to do in that case is we just need to add the 7 bits. Else, that's where the interesting part begins. Else, we need to set the 7 right to the 7 bits, but we also need to set the 1 bit that tells the algorithm that it needs to keep going. So we're going to bits.or the thing with 0x80. Right, and then we're going to what do you not like about this? And save crash with. There we go. That's the one I care about. Okay, once we're done with that, then we're going to call unsigned lib128 on the shifted number. And let's try that one out. So, okay, so what are we gonna do? We're gonna say, give me a buffer. We need a size of 3, hopefully. And then we're gonna go and leb unsigned leb 128 into that buffer the number 624485, and then we're gonna print the buffer. Okay, let's try that one. So 229, 142, 38. Now, how do we tell if that worked? So 28 is the last number. That's right. Does it give us the non? No. Can we maybe display these as hex numbers? That would make things a little easier for me. We're just logging it. Now, is there a way to JavaScript uint array 8? Is there a nice to string on this thing? We could write ourselves something, I guess. Something like this, maybe. And then we can do a array.for each. So this is a byte. And we need to, I'm gonna call it byte. And we need to string it as a hex. To string with the 16 in there, so b.to string 16, and then we're going to append this thing essentially. I'm going to say resp is this. Hopefully, I probably need to put those run that, and then we should log the result at the end. Let's see what that does. So E5 8E26. Okay, so that 0x plus 2 uppercase. I think like so. to uppercase. Okay, so 0x e5. So that looks good, right? So e5, 8e, 26. Okay, so we're doing right. We're doing well here. Now, one thing we note, like I noticed, is that for small numbers, this essentially returns just the number. So if I say 10, this should just give me a single byte, which is unfortunately not what's happening. Why is it writing a bunch of 0 bytes here? Oh, that's because this buffer has this size. And what we should really do is the same thing we did in the write to file impl over here. So we're gonna say used bytes here, which should just give us the 0xa now. Okay, that's good. And now can we we can probably map this actually. And then say like so. And then we can say the result is equal to or maybe we can just say we're gonna log this thing, done it like so. I'm gonna say numbers dot join like so. Let's try that. Okay, that's just a 0. Why is that so? Well, I no longer need this. Do I need to bracket this one up? Wait. What? Oh, is map just not implemented on these? Oh, right. Probably map doesn't. Yeah, well, map doesn't give you an array, right? Or like it doesn't let you do a type changing thing or something, maybe? Yeah, that gives you back a uint array. Damn it. Can I say, is it like a 2 array or something? Can I do array off? Sorry, I don't know how these things work in JavaScript, so kind of suck at this. Okay, so let's do array as this. Or like, let's say numbers is this. And then what we're going to do here is we're going to do a for each. But we're actually going to say numbers dot push this thing. Let's see if that works. Yay, JavaScript. And so if I go back to the example we had before, so the large one. Okay, that looks nice. Okay, so we got it. That was a bit of a long one, but okay. So now we can print our debuffers decently. It's possible that the brackets don't actually do anything. Yeah, we'll see. Okay, so where were we? You were up here. So this is an unsigned LEB 128 for the 32-bit integers that we have in JavaScript. Now we actually, if we were to do this right, we'd need to do this for big ints and allow int 64s. But I'm just going to not do that for now. And instead, I'm going to start to think about signed LEB, which is a lot harder than unsigned LEB, unfortunately. Well, a lot harder, but it's trickier. So let's do that. Okay. So how does that work? So signed LEB. Signed number is represented similarly, starting with an n bits 2 complement representation, where n is a multiple of 7. The number is broken into 2 groups as for signed encoding. For example, a signed number is encoded as this thing. But how do you tell? Oh, I see what's going on. Yeah, I see. That makes sense, I think. I think this makes sense. Okay, so let's think about this. I need to fix the signature, by the way. Just okay. So so let's say we start with the number. Let's say we do -2 for now, because that's easier. So if we were, oh God, so 2's complement works a little differently, right? It sets all the, I don't know, do you know how 2's complement works? Well, the first thing says in an int32, if you have a signed int32, the first bit, so the most significant bit, so the highest one, actually tells you whether or not this is a negative number. So if this is a 0, well, you get 31 bits of positive number. And if this is a 1, you get 31 bits of negative number. And you gotta take care of the edge there, because you don't want to end up, you only want to encode 0 once, so you usually get -127 to 128, and not 127 to -128, because you only need the 1 bit to encode the signedness, so you don't lose 2. You only lose like a single. Yeah, whatever. Really, the question is, what does this mean? Which is the tricky case, but let's not do that case. Let's say -2. That's actually this number. So -2 and 2's complement looks like this. What's the idea here? So the idea is that because this is a 0, the 1 at the front, this is a negative number, and so we figure out that this is a negative number, and then we flip every single bit in here. So this is now 0, 0, 0, 0, 0, 0, 0, 0, 0. That's the complement bit, right? 1, 0. And so this is the, and now this value is what this actually meant in terms of an integer. And so now this is a -2, okay? And so that's what this does. And now if we are to do this, to do the same encoding here, what we really need to check here, we checked if the shifted is equal to 0. Now we need to check if the shifted value is equal to a value that is all ones. What are we doing here? But no, we're going to shift in zeros from the left if we're not careful. What are they doing here? Is this using a logical shift, run arithmetic shift? While we've got more, give the low order 7 bits of a value, then we're going to shift the value by 7 if negative. So if the value is smaller than 7, no, smaller than 0 still. So the problem is that this is the thing this is talking about, like when it comes to a logical shift. So if we were to just shift this to the right by 4, we'd add just 4 zeros at the front and drop the last 4 bits over here, for example. But you can't do that, because what's going to happen here is that you've now turned this into a positive number when it used to be a negative number. So you need to, so a usual shift is actually going to preserve the signed bit when you shift signed numbers. And I think this is what this is doing, but I'm not entirely sure. So this is if the plane uses a logical shift, then we or equals with, what is this? I don't even know what this means. I'm so bad at all this byte shifty stuff nonsense. Okay, I'm gonna look at the Wasm implementation just for a second here. Lep 1 of 28 in Python. Test cases. Okay. Decimal in the first column, hex in the second column. Let's see. Once we've got an implementation to something, we can definitely push, see if we can just run it on all of these tests. The thing I'm really wondering about is how I preserve the thing, basically. Is this the complement operator? I think this is the complement, right? Tilde, I believe, just flips all the bits. Complement. Yeah, the complement is the tilde. Okay, so this is flipping all the bits on a 0 in this example here, which is right. So this is making a vector, this is making a number that is all ones. Then it's shifting it to the left by size -7. So it's shifting it to the left by, depends on the size. We're dealing with 32-bit ins, so we need to shift by 25. And then it ORs it, so it nukes that, it just sets everything, so it just sets the first 7 bytes to true. That's what that's doing. Understood. So this is only necessary for implementation of uses a logical shift rather than an arithmetic shift for a signed left operand. Now, if I look at this, I'm pretty sure this thing used a logical. No, it does not use a logical shift. It uses a logical shift here. Should we also use a logical shift in the unsigned case? We could. There's a well, there's this one, I believe, from bits. No? Oh, zero shift right. There we go. Is this something we should just adopt to JSF? Well, if we wanted to get this just done as quickly as possible, for sure. But I kind of want to understand what's going on. So that's kind of why I want to do this. It's because I kind of want to get better at bit fiddling. Exactly. We decided to understand what's going on. So this is using a shift right logical. I don't think we need that. I think we're just gonna shift right here. And if we find a case where this is the wrong case, we're gonna figure out soon enough. Okay, so let's just try this. Basically, we're gonna do the same thing as this, just without this case. Okay, so if exactly, we're gonna do a thing. So it's not a problem if it's negative. So if it's positive, if it's a positive number, we're just okay. I just need a second. I'll be right back. Actually, I'm really sorry, but dinner's ready. I'm kind of hungry. I will come back after dinner and keep going, but I totally understand. Of course, you're not going to sit around all that time. I'll just so the bit shifting takes a binary representation of a number, then bit fills it to make an LEB formative version of it. Exactly, that's what this is doing. I'll try to let you know when I'm going online again, and I don't know. I mean, if you still want to hang around, okay, so sure, just do your stuff then. Cool. Thanks for hanging out, man. Alex, this is it's kind of nice having someone to talk to during these. All right, I'll have dinner. See you in a bit.